Welcome to lecture 3 in Introduction to Applied Internet of Things. This is microcontroller part 2, and in this part we are going to discuss the Raspberry Pi Picos. There are two main versions, Raspberry Pi Pico and Raspberry Pi Pico 2, and both versions come with or without pre-soldered headers, or with or without a Wi-Fi chip installed on the Picos. We recommend that you use the WH version. That means that they have pre-soldered headers already from when you buy it, and it have a Wi-Fi chip on it. The specification from the two different versions, you can see that they have different microcontrollers. The first one is called RP2040 and the second one RP2350. You can also see that the version 2 have a slightly faster CPU. It have slightly more static RAM. It have more flash memory, but the rest are more or less the same. It have the same amount of general purpose input-output pins. It have more or less the same port and protocols, and as you see here, it both have a built-in temperature sensor that we will test out later on. The name RP2040 and RP2350, that means something. RP stands for Raspberry Pi, and the first digits are the number of cores on the processor. The second digit, a 0 or a 3, is a type of core. The first one is called M0 plus, and the second one is called M33. That's the 0 and the 3. The 4th and the 5 is amount of static RAMs. The 5 is just 1 over, but it's the double amount. You can calculate the number yourself using this formula. And the 4th digit is amount of storage that the Pico remembers when you power it off. This ain't the same as the flash memory, because the flash memory isn't located in the chipset, it's located on the Pico. The Pico have some features. In the upper area you can see the micro USB port where you plug your computer in. You can also see the onboard LED, so you can test your Pico even if you don't have any other sensor or devices. Under the LED you can locate the boot cell. If you hold it down while plugging the cable to your computer, this Pico turns into a USB mass storage device, and you can drag a new firmware over to your Pico and it will be installed. You can also see the chipset located in the center, and in the bottom area the metallic chip is the Wi-Fi chip. A good friend in this course is the Pico pinout diagram. The Pico have 40 pins. Several of them can be used in different ways. That's why you need a Pico pinout diagram. I print one out myself. So make sure you have a pinout diagram for your version of your Pico, if you have the version 1 or the version 2. They are more or less the same, but use the right one. In the upper right corner you can locate the V-bus. That's the directly connected micro USB voltage, and the VSys. The VSys number 39 and the ground 38 is how you power your Pico from external support. For example, a power supply or battery. The port 36 you can get 3.3 voltage out. Analog signals. Analog signals change smoothly over time and can have any value, just like in real life, things like sound or light. This means that for example in sound, a little louder or softer sound you can have that, and in analog signals you can also have a little lighter or little higher sound, signal. An analog signal can follow every tiny movement or shift, just like a hand-drawn line follows your pencil exactly. A digital signal don't follow every small change. Instead, they round it up to the nearest step. Like a staircase goes up in levels instead of in a smooth ramp. That means that digital signals are easier to store and easier to work with using computers, but they don't capture the fine details that are as well as analog signals does. To solve this, the Pico used something called pulse width modulations. Because some sensors, for example an RGB LED or a piezo buzzer, they need an analog signal to produce different brightness for the LED or different sound for the piezo. For example, the RGB LED have 3 different lights, a red light, green light and a blue one. And they want to adjust from 0 to 100% in fine details, not just 1 and zeros. That means that the LED can glow just a little or shine very bright, depending how strong the analog signal is. The Pico solved this using PWM or pulse width modulation. It tried to create an analog-ish like signal using digital signals. This by quickly switching between 1 and zeros and changing how long the signal stays in each state. A state could be 1 or 0. It can by using this technique, it can simulate different voltage levels. And the 2 things that are important is the duty cycles. It's a percentage of a cycle where the signal is on. And you can see on the right area a difference between 50 duty cycle and 25 and 75. We also have something called frequency. That's a number of cycles per second, and it's calculated in hertz. Sometimes we have the other way around. We have an analog signal that we want to convert to a digital one. And then we use the analog digital converter, ADC, that transform an analog voltage signal to a digital number that we can process. The Raspberry Pi Pico uses a 12-bit ADC. That means that the range of input voltage from 0 to 3.3 voltage calculates from 0 to 4095. But in most cases we will use a 16-bit value instead, and we will use some scaling for that one. It will work automatically. So in real life we will use not 0 to 4000, we will use 0 to 65,000 instead. Another feature of the Pico is UART, Universal Asynchronous Receiver Transmitter. We will test this device protocol for communicate between 2 different Picos. But you can also use UART for 1 Pico and a sensor, for example, if you use a sensor that are compatible with UART. UART uses 2 wires, one for receiving and one for sending, transmit and receive. The Pico have 2 different UART, UART 0 and UART 1, and the default pins are 0 and 1, and you use the 0 one for transmit and the 1 for receive. Another protocol we will use on a Pico is the SPI, or the Serial Peripheral Interface. This interface was invented in the early 80s by Motorola using a master-slave architecture. SPI is a way for microcontroller to communicate with other devices, for example sensor or displays, by sending data 1 bit at a time over multiple wires, usually 4 wires, not included power and ground. One wire for sending data, often called master out, slave in, and one for receiving, master in, slave out, and one for clocking, serial clock, and one for ship select, or sometimes it's called slave select. Another protocol we will test in this course is the integrated circuit, sometimes called I2C or I2C. It was invented by Philips Semiconductors in '82 and is widely used for attaching lower speed devices. I2C or I2C just uses 2 wires, and it allows multiple devices to share these 2 wires, each device having a unique address, making it quite simple to use many devices to communicate with your Pico. The pins or wires are often called SDA, serial data line, and serial clock line. The data line uses, as it sounds like, it sends or receives data from the master and the slaves, and the clock sends the clock signal to sync the data. Some devices can both use SPI and I2C. If you want to test the I2C, the proofs are that it just uses 2 wires, not included power and ground, making it simpler to connect, especially if you have a lot of devices. You can connect up to 127 unique addresses on the same 2 wires. But I2C is slower than SPI and can be complex if you have devices with the same unique address. So if you prefer SPI, it's faster. Of course, you have 4 lines instead of 2, but the 4 lines make it more complicated because you need 4 lines, and it's easier to connect just 2 than 4. So in short, you use I2C if you have a lot of devices but you don't need the fast connection with the SPI. If you need the fast high-speed communication, you should use SPI. In this course we will test both of them and see the difference. In the specifications you saw that the Raspberry Pi Pico have 2 hardware I2C ports, 0 and 1. It also have 2 SPI ports, 1 and 0. And if you look at the pinout diagram, you can see that you can change the general purpose input output pins depending what pins are free. But if you have already used 2, for example 2 I2C ports, then you can have a third one, a software port. It's called bit banging. It's a bit slower because it's no hardware support. You have to send signals manually from code. So if you have to have, for example, 3 I2C ports, you can use a software port, but it will be slower and it will use more CPU. But it's a good way to learn how to communicate with I2C or SPI. This was everything from this part. If you have any questions, please come to Discord and ask us, and good luck with the course.